experience a cloud just by walking around San Francisco. This fog is just a stratocumulus cloud where its base is at the surface. But we don't think of it that way. We think of fog as this gray kind of haze when it's actually just individual cloud droplets that are obscuring our view. I think if people realize they're walking through a cloud that's probably the most important cloud type on Earth, they might think that's pretty cool. Clouds are complicated because there's so many different types. Some are liquid, some are ice, some are both. Some grow all the way from the base of the atmosphere to the top. And there's seasonal timings to worry about. The biggest question that cloud physicists are investigating right now are how cloud droplets and aerosol particles interact with each other. Any particle in the atmosphere is considered an aerosol. You only make a cloud when you have a particle for the water vapor to condense upon. In general, if you think of a cloud over the ocean, the majority of particles that serve as the center of a cloud drop are usually this combination of sea salt and some biologically produced sulfur from algae. If we look over land, dust is a huge component, right? Because there's lots of dust over the desert, there's lots of dust over the land. And then for industrial areas, particles from, say, power plants or from industrial processes. Wherever you are regionally, the particle distribution changes. So places where there's lots of fires, our clouds have smoke centers, right? The smoke is actually amazing and complicated because it does two things. If it's on top of the cloud, like in San Francisco Bay, if I look down from space, the sunlight's coming straight from above, the smoke, it would look much darker, so it wouldn't reflect as much light back. It would actually heat the Earth in that sense. Now, eventually, the smoke can actually intermingle with the cloud, and not only does that change how the cloud behaves, it gives us a lot of other things to worry about too. It changes whether or not it rains, which determines how long the cloud will stay there. If we start infusing the cloud with more particles, we can have new particle formation and have lots of smaller ones, and now our cloud looks brighter because now we've got more droplets to reflect light. The stratocumulus example is great, where you'll have, actually off the California coast, it's actually very easy to see with the ships going to and from Hawaii. The ship track streak will be so much brighter and looks thicker and fluffier than the cloud near it. So when it's above, it makes the cloud look darker. When it's intermingled, it makes it look brighter. So it's a really complex system because you could have both happening at the same time. So how much does one cancel out the other is really complicated. You can see that added smoke and added particles from us doing something as a species is changing clouds. It's not just there's lightning and there's some fires. The amount of clouds that are on the Earth determine how much light is bounced back. If we get rid of those huge cloud masses, right, then there won't be as much energy going back to space and the overall temperature of the Earth would go up. We have to know why it is doing what it's doing right now so that we can be better informed about how to calculate what's going to change in the future, especially in regions that are developing. More people are doing farming, there's more particles being emitted, and then that could exacerbate the problem and maybe deplete the cloud, and then it gets warmer on top of that. The future of our work is to really get an understanding of those interactions across a range of aerosols and a range of cloud types. Clouds are that important to what temperature the Earth is that we need to know what those changes are.